So first thing I want to talk about today is reaction rates. Now reactions occur at several different rates. Some go very quickly, for an example an explosion, and some reactions go very slowly, something like rusting. As it turns out, something exploding and something rusting are the same type of reaction. They just happen to be the same type of reaction that occurs at a very different pace. So just be aware that we have fast and slow reactions. Now, the rate of a reaction is actually controlled by three primary factors. We've got concentration, we've got temperature, and we've got the structure of the molecules and the orientation of those molecules when they collide. Now we're going to look at each of these separately and take a look at the effect that each of them have on the rate of a reaction. So let's look first at concentration. Now reactions require collisions in order to occur. Now what those collisions do is they cause bonds to be broken, and a collision also has to happen in order for bonds to form. Molecules or atoms have to get close enough in order for those bonds to form. Now the higher the concentration, the more collisions you're going to have. And the more collisions you have, the faster the rate's going to be. So as concentration increases, reaction rate will increase. Let's take a look at temperature. Now with temperature, we know that collisions are needed to break and form bonds. Now the faster that molecules are moving, the more likely that they are to collide. And so the more they collide, the more likely they are to break a bond. So the higher the temperature, the faster molecules move, and the more they collide. So as temperature increases, reaction rate increases as well. Now if we look at orientation, when we talk about orientation, we're referring to the relative positioning in space of the molecules involved in a collision. There's a lot of molecules that require a very specific orientation during the collision in order to break or form the specific bonds needed for a particular reaction. So what that means is that not every collision between two molecules will in fact cause a reaction. Actually, most collisions that happen do not cause a reaction. Only the ones with the proper orientation based on the structure of those molecules will actually cause a reaction to happen. We can look at kind of a diagram of that. Some collisions have what we would say a very high orientation requirement, where there's a very specific place on that molecule where the collision has to occur. Some have a very low orientation requirement. So here we see a reaction. I wouldn't say if this is a high or a low. This is probably kind of a low reaction requirement. But we see that fluorine ion coming in. It hits that carbon atom between the hydrogens there. It causes that carbon-chlorine bond to break, and it causes the carbon-fluorine bond to form. And now rather than methyl chloride, we have methyl fluoride and a chloride ion. So as I mentioned in the previous slide there, most collisions occur without the proper orientation. If this fluorine atom were to hit maybe here, or collide with the hydrogen, or collide with the chlorine, it wouldn't actually be able to break that bond between the carbon and the chlorine. What has to happen is that fluorine atom has to collide with that carbon atom directly on the back side of that carbon chlorine bond in order to break it and then form that chlorine-fluorine bond. So this reaction does have an orientation requirement. It really is dependent upon the orientation of that fluorine-carbon collision. Let's take another look at reaction rate and how we might express it. Now, anytime we're looking at the rate of something, generally what's implied is some sort of progress measured by some unit of time. For example, when you're driving down the road, you have a speed, and that speed is really a distance rate. How many miles per hour are you traveling? And we just say miles per hour quite loosely without maybe thinking about what it really means. Now, for a chemical reaction, what we want to look at changing with time is something's concentration. It can be either a product or a reactant. So let's take a look at a reaction here where we've got a couple of iron ions reacting with a tin ion, and we're exchanging some electrons, and things are changing their charges there. Now, we're not going to really worry quite so much about the reaction itself, other than just some of the details from the reaction itself. So we start the reaction, and we're going to take a sample after 38.5 seconds. And what we see is we measured a product here. We measured iron 2+, and we see that it has a concentration of 0.0010 molar. Now what we can assume is that when the reaction started, that concentration was in fact 0. So we're going to look at the rate of the reaction as the rate of iron 2+ formation. And so that would be expressed as the change in the concentration of iron 2+ over the change in time. Well, the change in the concentration of the iron 2+ was 0.001 minus 0 because it started at 0. And that change took 38.5 seconds. So the rate of appearance of the iron 2+ was 2.6 times 10 to the minus 5 molarity per second, or molar per second. And that's a very common rate unit for a reaction. It may be molar per minute or molar per hour, but molar per second is also frequently seen. So in that example, we showed the reaction as a rate of appearance of a product. We can also express the rate as a disappearance of reactants. So really, if we think about it, we know that the iron 2+ can only appear as quickly as the iron 3+ disappears. So the change in the iron 3 concentration with time would be the exact same rate as the iron 2+ in this reaction. Only here we would use a negative sign to indicate that the rate was decreasing because the concentration is going down. So the change in the iron concentration, or iron 3+ concentration, was actually a negative rate because the concentration was going down. Just like in a car, if you were braking, you would express the speed as a negative speed since speed was going down. We see here a graph where we show a reaction of H2 plus I2 going to 2HI, and we have our HI concentration increasing. So this is our red line here, and we're measuring just a rate right here, measuring a change in time, and we have a change in concentration on the y-axis there. If we want to measure one of the products here in green, or one of the reactants rather, we would see that its concentration is dropping with time, and so it has a negative concentration, or a negative rate rather. Now we saw in that last example that we had a slightly different stoichiometry between the tin and the iron. And if we measured the rate of change in the concentration of the tin, we would have seen a different reaction rate based on what we measured. So the tin would have a different change in concentration than the iron did because it was being used up at a different rate based on the stoichiometry of the reaction. But what we want to make sure that we do is when we say this is the reaction rate, we want to make sure that we are expressing the same value for the rate, and it doesn't matter which reactant or which product we are actually using. We should get the exact same rate for the reaction regardless of which component we're expressing it as. So what we want to do is we want to find a way to indicate how each component changes relative to its stoichiometry. So the first thing we're going to do is we notice that the iron here and the iron here both have a 1/2 coefficient in front of it. And that's because their coefficient in the balanced reaction is a 2. And we see that the tin has no coefficient in front of it because their coefficient in the balanced reaction is a 1. So we use the reciprocal of the coefficient from the balanced reaction as a coefficient in front of the rate change. So this means that the overall reaction rate would be half the rate of change for the iron with respect to time, or equal to the change of the tin with respect to time. And since the iron rate would be twice that of the tin, and then we take half of it, that would give us the exact same value. It's very confusing to hear verbally, but when you work it out in problems, you'll see that it turns out exactly the same. Now notice also that we've got a negative sign in front of the iron 3 plus and a negative sign in front of the tin 2 plus. This is because they are reactants, and so their rate would be negative. So by changing the sign of the negative rate, we give it a positive value, which would match exactly the positive values got from measuring the rate as an appearance of products. And so regardless of which of these components we measure the rate with, as long as we use one of these forms for the rate, we will always have the exact same value regardless of which reactant or product we choose. And so there again, we use the inverse ratio of the coefficients. Reactants always get a negative sign for their rate. Products will always have a positive sign. So let's consider a reaction. A plus 3B goes to 2C plus 2D. We're going to carry out a reaction and take some measurements here. So at time equals 2 minutes, we measured that the concentration of B was 0.9986 molar. And at time equal to 15.2 minutes, we measured the concentration of B at 0.9746 molar. We want to know what the average reaction rate was during this time. Okay, so let's just take a look at how we would express the rate in terms of all the different components. We don't have to do this for this problem, but this just kind of helps us see how to write these reaction rates. So we would write negative delta A over delta T, because the coefficient of A is 1. That's equal to negative 1/3 change in concentration of B over change in time. And again, that 1/3 because the B is a reactant and it has a coefficient of 3. So the reactant part is why we have that negative sign. When we look at C, we have plus 1/2 change in C over time. And for D, plus 1/2 change in D over time, change in time. So we use those 1/2s because the coefficient of C and D are 2. And we use the positives because they are products. Well, we're going to worry about B for this one. So let's go ahead and take a look at this calculation. The change in concentration of B is going to be your final concentration minus your initial concentration. So we have 0.9746 minus 0.9986. So notice that we get a negative change in the concentration of B. Well, that makes sense. B is a reactant, and so its concentration is going to be dropping. We look at the change in time. Our final time was 15.2 minutes. Our initial time was 2 minutes, and so the change in time was 13.2 minutes. Now, if we wrap that all up, we see that rate is equal to negative 1/3 change in B over change in time. So we're going to get negative 0.0240 molar over 13.2 minutes. And we get an average rate during that time of 6.06 times 10 to the minus 4 molarity per minute. Now, if I had measured the concentrations of A, C, or D and plugged them into the appropriate equation, I should have calculated the exact same rate for that reaction. Let's take a look at reaction conditions, because there are different things that can affect the rate of a reaction. Some we talked about. We did talk about concentration, temperature, we haven't talked about the presence of a catalyst yet. We're going to do that here in just a little bit, as well as the surface area of any solid reactants. So how does each of these affect the rate? Well, we talked very briefly about concentration and temperature. We're going to talk about that in a little bit more detail. So when we're looking at reaction rate and concentration, when we're dealing in the field of kinetics, what we're really trying to do is to establish some sort of mathematical connection between the concentration of your reactants and the rate of the reaction. And this equation has to be determined experimentally, and it's something that we call the rate law. Now, if we have just some generic reaction where we have A plus B going to C plus D, and let's say our coefficients for all those different reactant products are little a, little b, little c, and little d, we can write a generic rate law or a general rate law for that reaction, saying that rate is equal to K times the concentration of A raised to some power m times the concentration of B raised to some power n. Now that K that's there, this is called a rate constant. And the exponents that we have there, m and n, notice that they are not part of the overall reaction. M and n are two values that have to be determined experimentally. We call m and n reaction orders. Well, what is a reaction order? Well, again, they're orders, they're exponents that we use mathematically to enable us to calculate the rate of a reaction based upon concentration of our reactants. The overall reaction order of a reaction is just the sum of those exponents. So let's say m and n are both 1. So if we were to raise two concentrations to the power of 1, then the overall reaction order would be 2. If we had a concentration that was squared and something that was raised to the first power, then the overall order would be 3, 2 plus 1. Now again, we have that m and n, and they were not part of the overall balanced equation. What we have to do is we have to do a series of experiments to determine what effect each reactant has on the reaction rate. And once we do that, we can find what the exponents are for that rate law. And so these experiments have a related name. They are called rate law experiments. So in lecture 5, we started looking at reaction rates and what affects those rates. And now we're going to start taking a little more quantitative look at reactions and reaction rates and try to determine these reaction orders, these exponents that are part of the rate law. And so what we're going to do is these things called rate law experiments, where we're going to change the concentration of one of our components at a time to see what effect that particular reactant has on the rate of the experiment. So here's an example equation. We've got mercury chloride and the oxalate ion reacting to give us some chloride ion, carbon dioxide, and mercury chloride. A little different mercury chloride. And we can write just a general rate law for this reaction. We've got rate equals K times concentration of HgCl2 raised to some power m times concentration of the oxalate ion raised to some power n. Now we have no idea what those exponents m and n are just by looking at the balanced reaction, and so we're going to have to do a series of experiments to determine what those exponents are going to be. So here's a very typical set of data that we would get from a series of rate law experiments. We can see that in going from experiment 1 to experiment 2, we changed the concentration of the oxalate ion, and we can see that the rate changed. And then in going from experiment 2 to experiment 3, we see that the oxalate ion concentration is now the same, and we only changed the mercury chloride concentration. And again, we see an example of, we see the rate change there. So again, we're always comparing two experiments at a time, and we do this to see what effect did changing the concentration of only one reactant have on the rate. Now, in order to do that, we have a fairly easy equation that we can just plug in our values for. We're going to compare the rates to the ratios of the concentrations, and that ratio of concentrations is going to be raised to some exponent, and the exponent that we find for this equation is going to be the exponent that we plug in for that particular reactant. Now, I don't have this one worked out here. We will work it out in class. I will also put it up on D2L as a pencast. Let's talk about this rate constant K. What it is a proportionality constant, like so many constants are. Once we have a rate law with the orders plugged into the equation, we can then take any of our rate law our rate law equations, or our rate law reactions that we've done for that particular reaction, and solve for the value for K. Now, any single experiment's data can be used. K is not as constant as we think a lot of constants are. With K, it's very condition dependent, and it does change with temperature. So as soon as the temperature of a reaction changes, we do have to do a new series of experiments and find a new value for K. And the units of K change, and so what we need to do is to relate concentration and time, and so the units for K are different depending on the orders of the different reactions. We don't ordinarily really worry about the units for K for reasons that are beyond the scope of this course, but I'll never ask you for the units of K. The key with K is that the overall rate must come out to be units of molarity per time, since that's the rate. It's a change in molarity with a change in time, so the rate has to have units of molarity over time. Now, sometimes what we want to do with a reaction is determine the concentration of a particular reactant or a particular product at a very specified time during a reaction, and in order to do that, we need to use things that are called integrated rate laws. So what we're going to do is we're going to relate concentration to time, and the rate law equation, the integrated rate law equation, is dependent upon the overall order of the reaction. Remember that overall order is the sum of any of the exponents that we found for the orders. Let's look at a first order reaction first. So in a first order reaction, the reaction rate and the rate law is directly proportional to concentration, and we get an equation that looks something like this, where the change in R over the change in time, or the change in concentration of a reactant over the change in time, is equal to the rate constant found from the rate law times the concentration of R. And this can be transformed into what we call the integrated rate equation using calculus. We're not going to go through the derivation here. I believe your book does, if you want to take a look at it. But what we end up with here is that the natural log of concentration of some reactant at time t over the concentration of that reactant at time 0 is equal to negative kt, where k again is the rate constant and t is time. Okay, so again, this little 0 here indicates that we have a time of 0, and this little t here indicates some t, or some time t. It can be any time that we want it to be. But the t here is equal to the t there. So here's an example. So we have natural log of RT over R0 is equal to negative KT. Let's look at some mathematical things here. This value here, RT over R0, because they're reactants, this ratio will always be less than 1, because reactants, as the reaction proceeds, will always go down, which means the greatest concentration is always at time 0. So since concentration of R at time t is always less than concentration at time 0, this will always be less than 1, which means that this whole term with the natural log will always be negative. This is why we have the negative sign here, to make sure that we have a positive value for k, and we can only have a positive time t. Now, if k is known, we can figure out how much time is needed to reach a certain amount of product. If we know the amount of time, we can figure out how much product we would have at that time. So it's a fairly flexible equation, and we can use it for a variety of things. Now, for this particular equation, for first order, k is independent of concentration, and the units for k here are going to be time to the minus 1. So here's an example. We have hydrogen peroxide decomposing in a sodium hydroxide solution. It's a first order reaction, so we're told it's a first order reaction, and we want to know what the concentration of the reactant hydrogen peroxide is after 100 minutes if the initial concentration is 0.020. We're given the rate law there, we're given the value for K, so all we need to find is the concentration of H2O2 after 100 minutes. And we're going to work this one out in class, and there will also be a pencast for this problem posted on D2L. Now, second order reactions, when we say second order, it means that the overall order of the reaction is second order, and we have two possibilities here. Either we have one reactant that is squared, so one reactant that's second order, or we have two reactants, each are first order. So two different ways we can do this. It does not affect the rate equation, and so your rate equation here is going to be negative change in reactant over change in time is going to be equal to K times concentration of that reactant squared. The integrated rate form, which is generally what we want to use, is that 1 over concentration of the reactant at time t minus 1 over concentration of that reactant at time 0 is equal to Kt. Again, since concentration of reactant at time t is smaller, this will be a larger fraction than this one, and so we always get a positive value over here. The units of K in this case are liter per mole time. Here's another example. Here we have a gas phase decomposition of HI. We know it follows a second order reaction, so we want to know now how much time does it take for the concentration of HI to drop from 0.010 to 0.0050. So we want to cut the concentration of HI in half at 443 degrees Celsius, and we're given the K value here. So again, this will be worked out as a pencast and posted on D2L, and we will also work it out in class. Now, zero order reactions are a little bit of an unusual type of reaction. So here the rate of reaction is completely independent of reactant concentrations. It means I have no exponents for any of the reactants. And so our rate equation here is negative delta R over delta T is equal to K times concentration of reactant raised to the 0 power. Well, anything raised to the 0 power is a value of 1, and so we have K times 1. So the rate of the reaction is dependent only on the rate constant K. And the integrated rate equation here is concentration of the reactant at time 0 minus the concentration of the reactant at time t is equal to Kt. And the units of K are molarity times time. That's not a minus sign, it's just a separator. Now we can also use graphical methods to determine whether or not a reaction is zero order, first order, or second order. And a lot of times what we have is we have concentration and time data. When you're doing an experiment, usually you know the concentration you start with, and you can measure concentration as you go through the reaction. And a lot of times you start a timer when the reaction starts, and so you have that time concentration data. So what we want to do is take those integrated rate laws and plot that data according to the different rate equations and look for the best fit. And so what we've done here is we have found a way to rearrange our zero order, first order, and second order equations as linear equations where we have a y value for each of these, an mx value, so remember m is slope times x, which would be your time component, plus some b, and b is some derivative of your initial reactant concentrations. But for a zero order, we would plot the concentration of reactant on time as time t, or concentration of your reactant at time t on the y-axis, and time on the x-axis. For a first order reaction, we would try taking the natural log of all the concentration of R at time t data plotted on the y against time on the x, or for second order, try 1 over R at time t versus t on the x. And we just see which of those plots gives us the most linear fit. The most linear fit will tell us what order that reaction is. Here's just some examples here. So here was some pressure data. So we are able to measure the disappearance of a reactant by looking at pressure. So we plotted log of p on the y and time on the x, and what we found is we got a nice linear equation. We know that for this reaction, based on the equation in the previous slide, that slope is equal to negative k, and so we find our negative k here, or find our slope, that's equal to negative k, so we find our slope, change its sign, and that gives us our value for k. We can do the same thing for a second order equation, or we plot some data, plot it as a second order. We see it gives us a nice linear fit, and so we know it's second order because the y-axis here is 1 over NO2 versus time, and we could do that plot. We get our value for our slope, and that gives us our k value there. And the first thing we're going to talk about is half-life, and this is a kinetics related topic. And the half-life of a reaction is really just the time it takes for a reaction to have its reactants to reduce their concentration by half. And it doesn't really matter where in the reaction it is, just from wherever you start to wherever you finish, the reactants will be cut in half. We very frequently use the starting point, but it doesn't necessarily have to be the starting point. So we see half-life indicated by T with a little subscript of a 1/2 to indicate half-time or half-life. And primarily we use it for first order reactions. We certainly can use it for zero order and second order. Our book talks about half-life for zero and second order as well as first order. We're going to focus primarily just on first order. Now, when we're looking at an integrated rate equation graph that we saw in lecture 6, we have that nice straight line where we have the natural log of our concentrations on the y and time on the x, and we can find our half-life anywhere on that first order graph. So we don't have to start at the beginning. We can look anywhere on our graph to find the half-life. The reason we can do that is because the half-life of a first order reaction is independent of concentration. It's dependent solely on K. And so there's our equation there. We have our half-life, which is equal to 0.693, which is actually the natural log of 2 over K. And so we see there that the concentrations of the reactants don't factor into the calculation for half-life at all. It's based solely on the rate constant, and as long as we keep our temperature the same, the rate constant remains the same, which means our half-life will remain the same. We can look at a graph of concentration versus time if we want, and there we see if we start at time 0 up here, we have a concentration of 1 molar, and so when we get to half molar, the time it takes to cut that concentration as half is the half-life. And so we see here it took 100 seconds in order to cut our concentration to 0.5, so our half-life would be 100 seconds. And what that means is that every 100 seconds, the concentration is cut in half. So we went from 1 to 5, and then we go from 5 down to 0.25, from 0.25 down to 12.5 or 0.125, etc. And it wouldn't matter where we start. If we look at the time at 0.75 here and went down to 0.375, we would see that would also take 100 seconds. So it doesn't matter what the concentration is to start. It's going to take 100 seconds in this case to go to half of whatever your starting concentration happens to be. Well, here's an example that we'll work out in class. It says for the decomposition of N2O5, the rate constant K is 1.7 times 10 to the minus 3 inverse seconds. How long will it take for a sample to decompose to 12.5% of its original value? And there's our reaction there, which isn't terribly important. But again, we will work this one out in class. So also related to kinetics is a thing called the Arrhenius equation, put forth by Svante Arrhenius. And what it really does is it relates reaction rates to inherent factors in the reaction. These are things that you can't really change. So we have the energy in the reaction, the collision frequency, the collision geometry, and the activation energy of the reaction. And here is the equation that relates all of those things together. We have K, which is the rate constant. So K is equal to this capital A, sometimes called an Arrhenius factor or a frequency factor. Sometimes it's called a pre-exponential. It has a lot of names. It's all the same thing. And then we have this large exponential term there. So we have E to the minus EA over RT, where EA is our activation energy. R is our regular gas constant, but this is going to be the 8.314 version since that uses energy, and then T, of course, is temperature in Kelvin. And so that exponential term really represents the fraction of molecules that have the minimum amount of energy needed in order to react. And got a little funny saying there in your face. Svante Arrhenius is an interesting historical character in terms of chemistry, and we'll talk about him in class just a little bit. Now, what is that term, that exponential term? Where does it really come from? Well, it has to deal with temperature and the energy in the collisions. So temperature is a measure of kinetic energy. It's not a measure of heat. And so if we think about temperature, or kinetic energy rather, kinetic energy is made up of mass and velocity. And so as I increase the temperature or decrease the temperature, really the only thing that can change there is the velocity. I can't change the mass of a material by changing its temperature, but I can change its velocity. So what that means is that raising the temperature of a sample causes those molecules to move faster. And or vice versa, adding heat causes those molecules to move faster, and that in turn causes the temperature to rise. So as those molecules move faster, they collide more often, and they collide with more energy. And so the reaction rate will go up. Now if we look at this little graph here over here on the side, so our EA there, some activation energy, which is an energy barrier really that molecules have to be able to meet in order to react. Now, this exponential for this fraction of molecules with a certain energy never goes to zero. So even if you have a really high activation energy, there's always going to be some small fraction of molecules that have enough energy. So you're always going to have a little bit of a reaction. But here in blue, we see this graph right here, and we see that there's only a small fraction of those molecules that have enough energy to get up and over that activation energy barrier. So the reaction rate will be sort of slow. Now if we look at temperature 2 shown in red, and it's in red because it's a warmer temperature than temperature 1, we see it here, and we see that the area of temperature 2 that goes above the activation energy is quite a bit higher than that of temperature 1. And so more molecules at the higher temperature have enough energy to get over that activation energy barrier, and as a result you're going to have a faster rate. So let's talk about activation energy in a little bit more detail here. As I mentioned, activation energy is this minimum amount of energy needed in a collision in order for molecules to react, and we indicate that by an E for energy and a little A for activation, so activation energy. Different types of reactions have different types of energy barriers, different activation energies. If there's a low energy barrier, that's going to mean that a lot of molecules are going to have enough energy to get up and over that barrier. So as a result, you're going to have a fairly fast rate. If you have a high energy barrier, well, that's going to mean that not very many molecules have enough energy, and you're going to have a very slow rate. And we describe these rates in a reaction coordinate diagram, which is going to show our energies both for the reactants and for the products, and then show graphically also this barrier that these molecules have to get up and over. And we'll take a look at that in this next slide. So RC stands for reaction coordinate, and if we look at it, this isn't a very quantitative graph, which is fine. Sometimes you'll see the energies for both the reactants and the products. You might see them listed over here on the y-axis. But reaction progress, you never really see. It doesn't necessarily indicate time. We don't use it as a quantitative measure of time, just reaction progress. So we pretty much go from reactants here to products here, and that's the end. However long that happens to be, it doesn't really matter. We're just looking at reactants to products. But this RC diagram does indicate where energies lie during the progress of a reaction. It shows the highest energy point during a reaction, which is going to be right up in here. And that's where we've got those bonds starting to break and starting to form during a reaction. Very high energy, well, it's the highest energy in that reaction, and the species that exists at that top energy has a couple of names. Sometimes it's called an activated complex, and sometimes you hear it called a transition state. So I'll generally refer to it as a transition state. It's that transition from reactants to products. So the energy from the reactants to the transition state is the energy for the activation energy. So we see that right here, our blue arrow going from the energy of the reactants up to this top hill. So the difference in those energies is going to be our activation energy. So how do we arrange all of this into the Arrhenius equation? Well, the Arrhenius equation has a couple of different forms. We're going to look at both of those. Mainly what we want to do with that Arrhenius equation is to rearrange it into a linear form, because linear forms just tend to be a little bit easier to work with. And it will also allow us to solve for the activation energy of a reaction. So here we have the Arrhenius equation arranged into a linear form. It's had a little bit of math done to it. But we have natural log of k, so our rate constant is going to be equal to negative EA over R times 1 over T plus the natural log of the frequency factor there. So that in essence is the Arrhenius equation. That's the linear form of the Arrhenius equation. We see the comparison down there below, how it lines up to a straight line. So if we graph the natural log of k on the y-axis and what do we got on the x-axis? 1 over t in Kelvin, then our slope is going to be negative EA over R. And so we can find our activation energy from the slope of that line. Now, one of the issues that you can have with that form of the Arrhenius equation is finding what that frequency factor is. And we can eliminate that frequency factor by taking a look at two temperatures and using a two-temperature form of the Arrhenius equation. And I'm not going to derive that out here. I believe it's done in your book. Or if you would just like to see how we go from a single temperature version to a two-temperature version, you can certainly come to my office hours and we can take a look at that. But here's the two-temperature version. We have natural log of K2 over K1, so that's going to be the rate constant at temperature 2 over the rate constant at temperature 1. And that's equal to negative EA over r times, and we've got 1 over t2 minus 1 over t1. Now this form of the equation is just slightly different from the one that you have in your text. The version in your text actually swaps out T2 and T1 here and gets rid of that negative sign. I don't like that form as much. To me, this one is a little bit easier to remember because the K's and the T's sound like they're in the same order. You have K2 over K1 and T2 minus T1. To me, that's just easier to remember, so that's why I like this version a little bit better. Either of them will work. Mathematically, they're identical. But when I teach it, I like to teach the K2 over K1, and then inside those brackets, T2 minus T1. They're easy to confuse, so you want to make sure that you get them in the right order. Well, here's an example of a two-temperature version. Here we have a rate constant for a reaction at 298 K, and what we want to know is what's the rate constant at 350 K, and we're given the activation energy. Any of those variables in that two-temperature version of the Arrhenius equation could be solved for. Here we're solving for second rate constant. We could have solved for second temperature if we wanted a certain ratio of rate constants. We could solve for the activation energy if we knew everything else. So just a lot of different options for what we want to solve for. But we'll work this one out in class. Now we're going to shift gears a little bit in our discussion on kinetics, and we're going to start talking about reaction mechanisms. Reaction mechanisms is really how reactants move from reactants to products. So let's take a look at this reaction here. This is just cellular respiration. We've got glucose there, C6H12O6, plus 6 oxygen molecules. It's going to end up giving us 6 carbon dioxides and 6 waters. Now this really is not likely to occur in a single collision. We would need to have the glucose molecule and all 6 oxygen molecules collide with the proper energy, with the proper geometry for all 7 of those things. So the likelihood is just really low, and if our lives depended on that collision happening, we probably would not be alive. So instead what happens is generally a series of small steps, simple two-bodied collisions, and we call these small steps elementary steps. So we generally have 2 molecules colliding. Occasionally we'll have 3 molecules colliding, but we always try to work it with 2 because 2 things running into each other is much more likely than 3 things running into each other, because the collision for 3 things would have to be those 3 things meeting at the same time, at the same point in space, with the proper geometry. So we link together a series of these steps, and we show exactly how reactant molecules become products through this series of steps, and this is what we call a reaction mechanism. So here's just a simple version of a single step mechanism. We have A2 plus B2 going to 2AB. We have the collision there between the A2 and B2 molecule. They break the AA bond, the BB bond, and they form 2 new AB bonds. So that would be a single step mechanism. Here's another version of that exact same reaction shown in 3 steps. So we have 2 A2 molecules running into each other. One of the A2s break apart. One of the A atoms then grabs onto a B2 molecule, making an AB2 species. That AB2 reacts with the other A that was formed in step 1 and forms 2AB. So there we see 2 different versions. We see a one-step mechanism and a multi-step mechanism. I start off talking about rate laws and elementary steps. So elementary steps are things that can help us find a rate law, and vice versa. A rate law can help us determine an elementary step in a mechanism. Now, when we have a mechanism, a proposed mechanism, we can write a rate law for each individual step in that mechanism, and we can do that directly from the coefficients for the different reactants in that step. This is not something that we can do for an overall reaction, but we can do it for an elementary step. Let's take a look at some examples here. So we're going to assume that these following reactions are just elementary steps within a mechanism. This is not just a mechanism, these are just individual steps from different mechanisms. So for that first one, where we have A going to B, we would write the rate law for that step as rate equals K times concentration of A. For A plus B going to C, we would write rate equals A, K times concentration of A times concentration of B. Again, because A and B are reactants, they have no exponents because the coefficients for A and B are 1. So technically the coefficients for the concentrations of A and B are also 1. And then for that third one, where we have 2A going to B, we say that the rate is equal to K times concentration of A squared. And again, that one is squared because of the 2 here that corresponds to that exponent there. Again, we can only do that for elementary steps. We cannot do it for an overall balanced reaction. So just to reiterate that there, rate laws can be written for each step in a mechanism directly from the coefficients of the reactants in those individual steps. But again, cannot do this from an overall balanced reaction. So you want to make sure you don't get into that habit. Let's take a look at a reaction here. We have 2NO plus O2 going to 2NO2. Now we see that we've got just three bodies in the reactants, 3 molecules there. So it is possible that it's a single step reaction. However, it's not very likely, just because that would mean that we'd have a 3-bodied collision leading to products. It is possible. That does happen, but it's not the likeliest circumstance. Now let's say also that we have a little bit of some experimental data, and during the course of the reaction, the species N2O2 is detected during the reaction. Well, if it were a single-step reaction, then we would never see this species N2O2. We would only see NO, O2, and NO2. So since we see N2O2, that means our single-step possibility is gone, and we have to start from scratch, and we have to build a multi-step mechanism. So let's just take a guess at a two-step mechanism, and we'll use what we know. The only thing that we really know is that we have N2O2 serving as a reaction intermediate here. So we're going to have 2 of our reactant molecules from the reaction, our 2 NO molecules. They're going to collide and kind of fuse together and make an N2O2 molecule. Then that N2O2 molecule is going to react with the other reactant, O2, and that'll give us 2NO2. Notice that both of these steps in the mechanism are balanced, and that's very important. Your individual elementary steps do also have to be balanced reactions in and of themselves. Now, to make sure that this mechanism adds up to the overall reaction, if there's anything in the products and in the reactants, it's something that we can cancel out. So here we see we have N2O2 in the products of the first step, and we have N2O2 in the reactants of the second step, and so those cancel out, and what we're left with is 2NO plus O2 going to 2NO2. So here the elementary steps add up to the overall reaction, and that is something that must happen. The sum of your elementary steps has to be equal to the overall reaction, and it has to be balanced as well. Notice also we saw N2O2 appears and disappears during the course of the mechanism, and when that's the case, we have something that's called a reaction intermediate. So it has to happen in that order. Something appears as a product and then disappears as it gets consumed as a reactant. That's what we call a reaction intermediate. So we have a reaction intermediate N2O2. This was something that was observed experimentally. Our mechanism adds up to the overall balanced reaction, which means that this mechanism is possible. It's not necessarily correct, but it's not wrong yet. So we would have to do more studies to prove that this mechanism is correct. However, at this point, it's still a possibility. Now, when we create a mechanism, there are two conditions that have to be met in order to make it a possibility, and we just saw those in this mechanism there. The sum of the steps have to match the overall balanced reaction. That's important that the sum is balanced. So once you add up those steps, you have to get the overall balanced reaction. And the rate law for one of those steps in the mechanism, remember you can write a rate law for each individual step, but one of those rate laws has to match the experimentally determined rate law. Now the step that does that is going to be the slow step in the reaction mechanism, and we're going to call that the rate determining step. The reason it matches the rate law for the overall reaction that you find experimentally is because that one step determines the rate for the entire reaction. Let's explore these reaction intermediates just a little bit more detail here. These are species, as we saw, that appear first in a mechanism and then they disappear. So they're generally a very high energy species. Usually that means that they're going to be very unstable. Species that are unstable tend to be very reactive. Because they're very reactive, they react very quickly with other things in the reaction mixture, which makes them very short-lived. Because they're short-lived, they can be very difficult to detect. If you find a reaction intermediate that supports a mechanism, that's really good. Just because you didn't find it doesn't mean that your mechanism is wrong. It just may mean that you can't detect those reaction intermediates. So a little bit of a double-edged sword there. But they can support or disprove a proposed mechanism. So again, we saw that if your mechanism has a particular reaction intermediate in there, and you find that intermediate that lends support to your mechanism, if you find a species during the course of a reaction that is not predicted by your mechanism, then your mechanism is no good and you need to start from square one. Let's look at an example. We're going to look at the decomposition of hydrogen peroxide, H2O2. Follows this reaction. 2H2O2 goes to two waters and an oxygen. We see that it is catalyzed by the addition of the iodide ion. It's quite an exciting reaction, actually. The experimental rate law, when you have the I minus as a catalyst, is rate equals K, concentration of H2O2 times concentration of I minus. Now, if we look at the overall reaction, we see, well, that would be a bimolecular reaction, just the two H2O2 molecules colliding. So we may think that that could be a single-step reaction. The problem is when it's catalyzed like that, and we have I minus showing up in the rate law, we know now it can't be a single step since I minus does not show up in the overall reaction. And so we're going to have to create a mechanism that has at least two steps where I minus is part of that slow step, because then it's going to show up in the rate law. So let's just propose a mechanism. We're just going to propose a simple two-step mechanism here, and let's see what we get. So for step one, let's just say we're going to make step one the slow step. Because we have H2O2 and I minus in our rate law, we're going to make those the reactants of our first step. So we're going to have H2O2 plus I minus going to water and a species IO minus. And we would write a rate law for that. Rate equals K1, concentration of H2O2 times concentration of I minus. We just write K1, that just indicates that that's the rate constant for step number one. Now in step number two, we know we need another H2O2 molecule in our reactant, since there's two in our overall reaction. So we have going to add another H2O2 molecule. We need to get rid of that species IO minus that step one produced. And so we're going to react H2O2 and IO minus, and that's going to make another water, an oxygen, and regenerate that I minus. Now here, again, if we assume that first step is the slow step, we see that the rate law of that first step matches the experimental rate law. Okay, so this is a viable mechanism, and you would find if you add up these steps, step 1 and 2, you will get the balanced overall reaction. You'll get 2H2O2 going to 2H2O plus O2. Now there's a couple of species in our mechanism that serve different purposes that don't show up in the overall reaction. Notice our I minus was used in step 1 as a reactant, and then it was spit back out as a product in step 2, and so it would cancel out. This is how a catalyst would appear in a mechanism, first as a reactant, then as a product. Notice also we've got the IO minus. It was first produced as a product and then consumed as a reactant in step number 2. This is how a reaction intermediate appears. They are different. A catalyst is something that we have to physically add, so it will show up first as a reactant, then get regenerated as a product. Reaction intermediates get generated as a product first, and then used up as a reactant later. Let's try a little bit more complicated example. It's easy when you're writing reaction mechanisms to write that slow step first, because very often you know the experimental rate law, and you just generate your first step from that rate law. But that doesn't always happen. The slow step does not always occur first. If a slow step happens after a fast step, then as that slow step is trying to proceed, the fast step kind of backs up, and as a result you have a buildup of the products in that first step. They can react with each other and reform reactants, and eventually that faster step reaches a state of equilibrium, waiting for that slow step to continue. So let's take a look at this reaction here. H2 plus I2 going to 2HI. For a very long time it was thought to be a single step reaction, and it makes perfect sense as a single step reaction. This experimental rate law is rate equals K, concentration of H2 times concentration of I2. If this happens in a single step, H2 plus I2 going to 2HI, that would also be the rate law for a single step. And so the rate law and the rate law for a single step mechanism agreed, and so it made sense that this would be a single step mechanism. And it's only a two-bodied collision, so that's fine too. However, what was discovered is that there was a reaction intermediate, and that these were I atoms. And so as a result, a two-step mechanism was proposed. We have I2 breaking apart to two I's, so their I2s are colliding and forming two I's. So as a fast step, it reaches equilibrium. And then those two I's react with an H2 molecule to give us our two HIs. Now, because we have a termolecular collision there in that second step, you've got a three-bodied collision taking place. That is a very slow step. We have these I atoms, iodine atoms, as intermediates. They're produced in step 1, consumed in step 2. But this situation here where you have a fast step followed by a slow step makes our rate law a little bit more complicated. So let's take a look at that. And this is going to get just a little bit messy. Now, since that second step is a slow step, we can write the rate law for that step as this. We have rate equals K, in this case K2 because it's step 2, times concentration of H2 times the concentration of I squared. It's not an I minus, it's not an ion, it's iodine atoms. These are high energy species. They don't exist for very long. It can be very difficult to measure the concentration of these I atom intermediates very well because they're high energy. So what we want to do anytime we're dealing with a rate law, we want to rearrange our rate law so that we can express it in terms of concentrations of reactants. We never want to have reaction intermediates as part of a rate law because they're very difficult to measure. Now, because that first step is an equilibrium, what we want to do is take a look at these forward and reverse reaction rates. And this is where our other reactant is, our I2. So we can write for that first step, K1, it's the forward rate constant, times the concentration of I2, is going to be equal to K minus 1, so that's the K for the reverse reaction, times I, concentration of I squared, because we had two I's as the reactants for the reverse reaction. We have to square that I there. So we can rearrange this to concentration of I squared is equal to K1 over K minus 1 times concentration of I2. Now we left that as I squared because in the rate law that we're trying to substitute into, we have the concentration of I squared. So here we have I squared here, and we left it that way so that we can substitute into this I squared up here. Now we're going to substitute in that value for I squared into our original reaction rate law. So we get rate equals K2, K1 over K minus 1, concentration of H2 times concentration of I2. Now we have a K times a K divided by another K. Those are all constants, and so constants times constants divided by constants is just another constant. So we can rewrite our reaction rate law as rate equals K, concentration of H2 times concentration of I2. Again, it gives the appearance that this is a one-step mechanism, but in fact, it is not. Now we've used this term catalyst a couple times, but we haven't really defined what they are and what they do for a reaction. So what we do is we add catalysts to a reaction in order to increase the rate of that reaction. And a catalyst isn't something that's it's not a label, or it's not something that defines a material. Catalysts are very specific to individual reactions, and so if you have a reaction that you want to make go faster, you have to try to find the material that will work as a catalyst for that particular reaction. Now, some of their characteristics is they're not consumed during the reaction. So they do get used by the reaction, but then they are regenerated. We saw that in the reaction mechanism. They're consumed and then spit back out. So many times catalysts are very precious metals, very expensive, and that's okay because they're always regenerated by the reaction. So catalysts can get used again and again and again. Now the way that they work generally is by lowering the activation energy of that reaction mechanism. So they change the reaction mechanism, and as a result the activation energy is lower. We saw in the last lecture that a lower activation energy is going to lead to a faster reaction because more molecules will have enough energy to get up and over the activation energy barrier. Here's just a simple graph of a catalyzed and uncatalyzed reaction here. We have in blue our regular uncatalyzed reaction here. You can see we've got quite a large energy to make for the activation energy there. But for our catalyzed pathway, we have a couple of different transition states, and that's not unusual, but you can see they're much lower in energy, and more molecules are going to have enough energy to get up and over that barrier. And so to get over that first barrier, our activation energy would just be right there. So it's in this case less than half of what we see for the uncatalyzed state. So chances are it's going to make the reaction go more than twice as fast. So let's talk about what equilibrium is and how we study it, how we understand it, and ways that we can actually manipulate it. So if you go back and look at a lot of the reactions that you've done up to this point in both semesters that you've had of chemistry so far, you'll notice that a lot of times we draw our arrow for our reaction in a single direction. Well, as it turns out, very few reactions only go in one single direction, and we saw a little bit of that here in this last lecture in kinetics. What we can also see is collisions between product molecules that can recreate reactants, and so products re-react and form reactants all over again. So as a reaction moves in the forward direction, well, what happens to that? So if we start with just reactants and move a reaction in the forward direction, what we get is those reactants reacting, forming products, and as a result we have fewer reactant molecules present, and so as we've seen, that forward reaction rate slows down. But as that forward reaction rate slows down, because of fewer reactant molecules, what we're making is product molecules, and so we're increasing the number of product molecules, and as a result, the reverse reaction rate begins to increase. So we have the forward rate decreasing and the reverse reaction rate increasing. At some point during that reaction, the forward rate and the reverse rate will be equal, and the reaction will have reached a state of what's called dynamic equilibrium. Now, at that point, the concentrations have stopped changing, but that doesn't mean that the reaction has stopped. The molecules have not stopped moving around, they have not stopped reacting. It just means that the concentrations have stopped changing. Now, when we see this, the term equilibrium, one of the common misconceptions people think is that the concentrations of products and reactants are equal, and that just isn't true. The equilibrium is referring to the reaction rates, and the reaction rates are equal both in the forward and the reverse direction. So when we write that a system is in an equilibrium state, we indicate that with a forward and reverse arrow, as we see here with A and C. And so forward and reverse arrow. If you want to see how equilibrium is expressed mathematically, we can do that using what we've learned from our kinetics chapter. We know that for equilibrium to be reached, we have to have the forward rate equal to the reverse rate. So we say rate forward is equal to rate reverse. Well, we learned how to express the rate in terms of the rate constant and concentration, and here we're going to use our just an example reaction of A turning into C, that reaction in equilibrium. So the forward rate can be expressed as the forward rate constant, K forward, times the concentration of A, and the reverse rate constant, or it's going to be equal to the reverse rate, which is equal to the reverse rate constant, K reverse, times concentration of C. Well, let's rearrange that and put all of our rate constants on one side and our concentrations on the other. So we have K forward over K reverse is equal to concentration of C over the concentration of A. Now we see that we've got two rate constants there, K forward and K reverse, and so K divided by AK is going to lead to another K. One constant divided by another constant gives you yet another constant. So that value is in fact a constant. And those concentrations for C and A are going to be equilibrium concentrations. These are not initial concentrations where the reaction started. These are going to be equilibrium concentrations where the reaction has finished up when it reaches equilibrium. Well, we're going to call that ratio of the forward rate to the reverse rate K equilibrium. And notice that it's a capital K, and we have a little EQ down there to indicate equilibrium. As the semester goes on, we'll have several different equilibrium constants, but they all follow the same basic premise. We're going to have products over reactants. Okay, so here we have C over A. It was A turning into C. So it's a concentration of products over concentrations of reactants. It'll get a little more complicated than that, but not by much. Let's look at a little bit more complicated reaction here. It's still generic. So we have A plus B going to C plus D. And our small a's, b, c's, and d's, those are just our stoichiometric coefficients from the balanced reaction. So for a balanced reaction, we can write our equilibrium constant expression directly, which is very much different from what we learned in kinetics. So, but for equilibrium, we can do this. So the equilibrium constant, KEQ, is equal to products over reactants. And so we have the concentration of component C raised to the power of its stoichiometric coefficient from the balanced reaction, so little c. And then we have times concentration of D raised to the little d. So it's my products over my reactants. So we have concentration of A raised to little a times concentration of B raised to the little b. Let's look at it for an actual chemical reaction here. We've got N2O4 in equilibrium with two NO2s. So products over reactants. So we have KEQ is equal to concentration of NO2 squared over concentration of N2O4. It's just that easy. Now the equilibrium concentrations are very important. They can vary within a single reaction depending on what starting concentrations were, but the most important thing about equilibrium is that that ratio must always hold true. And so here's a table for the reaction H2 plus I2 goes to 2HI. And we have our equilibrium constant expression there. It's going to be concentration of HI squared over concentration of H2 times concentration of I2. Now notice here we have several different types of initial concentration situations and different equilibrium concentrations as well. So in this first reaction, both H2 and I2 started at half molar. They finished at certain equilibrium concentrations, and what we find is that the ratio of those, when plugged into the equilibrium expression, we have an equilibrium constant of 50. Now, in the next one, we started with no H2, no I2, and half a mole or half molar HI. We find a very different set of concentrations at equilibrium for the H2, I2, and HI, and yet we still end up with an equilibrium constant of 50. On the third example, we have half molar concentrations of all species, and we have different values for the equilibrium concentrations again, but once again, those concentrations plugged into the equilibrium constant expression gives us a ratio of 50. So this value must be met, and that gives us a lot of power when we're looking at equilibrium constant expressions, the equilibrium constants, and what we can relate to them. And we'll see this as we move along, how it can help us. What does the value of that equilibrium constant tell us? Well, we can have it tell us where that equilibrium lies. What can I expect to find inside my reaction vessel once that reaction reaches equilibrium? So if the equilibrium constant K is much larger than 1, and here's an example of ozone turning into oxygen, it's got an equilibrium constant of 2.54 times 10 to the 12th, that's a lot larger than 1. What we're going to find in the reaction vessel at equilibrium is a lot more product than reactant. So for this type of reaction, we would say that the reaction favors the products. If K is much smaller than 1, so here's an example where we have a chlorine molecule breaking apart into 2 chlorine atoms, has an equilibrium constant of 1.4 times 10 to the minus 38. Very, very tiny number. What this means is the reaction really doesn't like to happen, and you have very little product form. So for this reaction, we would say that it favors the reactants. If a K is in the vicinity of 1, then what you're going to have left is a mixture of reactants and products present, and neither products nor reactants are favored in this case. And again, at equilibrium, you're going to have a mixture of both reactants and products, and you're going to have substantial amounts of both of those. Now there are some special cases when we're writing equilibrium constants, and we've talked about these just a little bit. I'll reiterate them here. So anytime we have a reaction that involves pure liquids, especially water, it seems to show up a lot in these reactions, or if we have a pure solid indicated by an S in our reaction, we leave those out of our equilibrium constant expressions. Now the reason for this is that these two phases compress very little with a change in pressure or even with a change in temperature. So the concentration of a pure liquid or a pure solid is generally based on the material's density. That determines the number of moles in a certain volume of a substance, and so because that's a constant value, we work that constant into the equilibrium constant already, and we don't have to worry about it. So when we are writing our equilibrium constant expression, we leave out any liquids and any solids. Let's take a look at some examples of that. So here we've got acetic acid in water dissociating into the acetate ion and hydronium ion. And when we write the equilibrium constant expression, we just have products over reactants, but notice that we have left out the value for the concentration of water. Concentration of water is a constant. It's somewhere in the range of 55, and so that's already worked into the value for Kc, and so we can leave it out of the equilibrium constant expression. Let's look at another one here. So the decomposition of calcium carbonate solid, it decomposes into calcium oxide solid and carbon dioxide gas. And again, when we write the Kc here, it's just the concentration of CO2. We've left out the calcium carbonate and the calcium oxide because those are solids. That means their concentrations don't change and their values are already worked into the value for Kc. An important concept in equilibrium chemistry is this idea of a reaction quotient, and we just call that QC. You could call it QP if we're calculating for gases. It's very similar to the Kc. The only difference is that when we're calculating an equilibrium constant value, Kc, we're assuming that the concentrations we're using are equilibrium concentrations. When we're doing a QC, we don't make that assumption. So we just use the concentrations at hand, and then we can use that value to determine if the reaction is at equilibrium or if it has to shift more to the right to get to equilibrium or to the left to get to equilibrium. So we can use the value of Kc to determine which direction that reaction has to move to reach equilibrium. Well, let's look at a reaction here, H2 plus I2 going to HI. We would write an equilibrium constant expression here as Kc is equal to Hi squared over H2 times I2. And again, because this is an equilibrium constant expression, we are assuming that those concentrations there are equilibrium concentrations. We write our QC expression in the exact same way. The only difference is the concentrations there don't have to be equilibrium concentrations. They can be any concentrations at any time t. And then we're going to compare the value that we get for QC with the value we get for Kc. So let's take a look and see how we do that. So if we calculate a value for QC and it's greater than Kc, that indicates that the products in the numerator are more abundant than they should be at equilibrium. And that means that the reaction needs to move towards the reactants, or it needs to move to the left in order to reach equilibrium. Vice versa, if QC is less than QC, that means the reactants are more abundant than they will be at equilibrium, or you can think of it as we don't have enough product than we should to reach equilibrium. And so that means that the reaction is still moving in the forward direction in order to reach equilibrium. So we would say that that reaction is shifting right. And if we find that our value for QC is equal to Kc, well, that means that our concentrations are in fact equilibrium concentrations and the reaction is at equilibrium. Let's look at an example using our H2, I2, and HI system there. So we have a Kc value for this reaction at 54.3. It's something that we would look up. And so we have this reaction taking place. We took a sample from this reaction and analyzed it, and we found the following concentrations. So what we want to know is the reaction at equilibrium? And if it's not at equilibrium, which way does it need to shift to reach equilibrium? Or you could say, which way does it still need to proceed to get to equilibrium? Well, let's find a value for QC. We know the value for Kc. So we see we have Hi squared over H2 times I2. Plug in our values that we found, and we find a QC of 111. Now, a value of 111 is greater than the equilibrium constant, so this reaction has too many products, and as a result, we have to, the reaction is going to be moving to the left. So you're going to have more collisions of product reforming reactant here in order to reach equilibrium. Well, equilibrium concentrations can be a little bit difficult to find, but as it turns out, we do have some techniques that if we know the equilibrium constant for a given reaction, and we know the initial concentrations of the reactants, we can calculate what we would expect the equilibrium concentrations to be. The technique that we use is called an icebox, and ICE stands for initial concentrations for I, the change in the concentrations for C, and the equilibrium concentrations for E. So let's take a look and see how we set one of these up. So we'll just use a very simple example here. A turning into B, and it's at equilibrium, has an equilibrium constant of 24. So my initial concentration of A is 0.850 molar, and we're going to assume B is 0. And what we want to know is what are the values of A and B at equilibrium. So here's our icebox here. We start out with an initial concentration of A at 0.85, an initial concentration of B at 0. Now our change in concentration, we don't know what it's going to be. We don't know how much this reaction is going to move in the forward direction. So we're going to say that the change is X. And since A is going to be turning into B, we have a change of minus X for the A. We're going to lose some amount of A as it turns into B. And then we're going to gain some amount of B, so we write plus X. Because we have a one-to-one stoichiometry, for every X amount of A lost, we're going to gain X amount of B. And so then the equilibrium box there is just the sum of the initial and the change. So we have 0.85 minus X for our equilibrium concentration of A, and for B we just have 0 plus X, or X, for the equilibrium concentration of B. We set up our equilibrium constant expression. Kc is equal to concentration of B over the concentration of A, and that's equal to the value of 24 as given to us in the above problem there. So now we take our equilibrium concentrations of A here, we plug it in there, take our equilibrium concentration of B and plug it in there, and we get X over 0.85 minus X. We multiply both sides by 0.85 minus X, solve for X, and we get a value for X of 0.816 for the concentration of B. Okay, we see that the concentration of B is equal to X, so once we find the X, we automatically know the concentration of B. Now to find the concentration of A, that's equal to 0.85 minus X, so we have 0.85 minus 0.816, and we see that we end up with a concentration of A of 0.034 molar. Well, let's look at an example that's a little bit harder here. So here we have a reaction, H2 plus F2 going to 2HF. It's got an equilibrium constant expression, or an equilibrium constant value of 115. Our initial concentrations of H2 and F2 are 1 molar and 2 molars. And what we want to know are what are the equilibrium concentrations of each component. So we want to know the H2, F2, and the HF. Now when we write our icebox, we have to take into account the stoichiometry. Our initial concentrations are just what are given by the problem. So my initial concentration of H2 is 1 molar, initial concentration of F2 is 2 molar, my initial concentration of HF is 0. If you're not given anything, you can assume that's going to be 0. Now, in the change, again, here's where we use the stoichiometry. We're going to lose some X amount of H2. Since there's a one-to-one stoichiometry between H2 and F2, I'm going to lose X amount of H2. I'm going to lose the exact same amount of F2, so minus X there as well. But for every H2 lost, I gain 2 HFs. So if I lose X of H2, I'm going to gain 2X of HF. And so now we just add up our initial and changes to get our equilibrium boxes, and we have 1 minus X for the H2, 2 minus X for the F2, and 2X for the HF. I plug those into my equilibrium constant expression, so I have HF squared over H2 times F2. Okay, don't forget to square that concentration of HF because it has a 2 coefficient in the balanced reaction. So now I plug in my 2X value for the HF, 1 minus X for the H2, 2 minus X for the F2. And this starts to get a little bit on the messy side. So there's our equation. We've got to do, we multiply everything out, we FOIL that bottom part, we multiply over by the 115, we can combine all of our terms, and we get a quadratic. 111x squared minus 345x plus 230 is equal to 0. Ew. So using either the quadratic equation that you learned in high school or a solver function on your calculator, you should reach 2 roots for this equation. Every quadratic has 2 roots. So we get a value of x of 2.14 or a value of x of 0.968. That second value is the only one that makes sense. Reason for that is if you look at our concentration of H2, we only started with 1 molar, so I can't lose 2.14 molar from the H2 because I just don't have that much. So we take that value of x, 0.968, and we solve for our other concentrations. So the concentration of H2 at equilibrium was equal to 1 minus x, so that ends up at 0.032. F2 was 2 minus x, so that ends up at 1.032. And the concentration of HF was equal to 2x, and so that goes to 2 times 0.968, which is x, and we get 1.936 for HF. And now an even harder type of equilibrium constant problem. So here we're given number of moles of NaCl. They're placed into a 1 liter flask. So we're not given the concentration, but we're given the number of moles and we're given the volume, so we can calculate the concentration. Since we just have a 1 liter flask, the number of moles of NaCl are going to be equal to the concentration of NaCl, since 0.5 divided by 1 is going to be 0.5. So we're given a Kc here, and it's pretty small there, 1.6 times 10 to the minus 5. So we have a decomposition where we have 2 NaCl's going to 2 NO's plus Cl2. Let's set up our icebox. We have 0.5 molar NaCl, no NO, and no Cl2. So our change here, we're going to lose 2x amount of the NaCl. So we're just going to use the stoichiometry there. So we lose NaCl. It becomes 2x of the NO and x of the Cl2. Again, notice that the coefficients in front of my x are equal to the coefficients that I use for my balanced reaction. That's a really good way of keeping those straight. So at equilibrium, I have 0.5 minus 2x for my NaCl, 2x for my NO, and x for my Cl2. So we set up our Kc expression here. We have 1.6 times 10 to the minus 5 is equal to NO squared times Cl2 over NaCl squared. So I plug in the values from the equilibrium side, the equilibrium row in my icebox. So I have 2x squared for NO, x for Cl2, and 0.5 minus 2x squared for the NaCl. So we start with this equation here. If we were to square that bottom term and collect all of our terms, up top we see that we're going to have a cubic equation result because we're going to have 4x cubed up top. You can plug a cubic equation into a solver in your calculator if you have one, but the potential for error is fairly large, making sure that you've collected all of your terms properly and gotten everything plugged into the calculator correctly. We're going to use a slightly different method where we make an approximation. We see that the value of k is very small, 1.6 times 10 to the minus 5. Because of that, that means I make very little product. Well, if you remember, x is the amount of NaCl being lost and the amount of product being made. So this means that x is most likely also very small and probably a lot smaller than 0.5. So we're making the assumption that 0.5 minus 2x is probably still approximately equal to 0.5. To our two significant figures, there's a good chance that that's correct. We'll always check it in the end to make sure our assumption was correct. But for now, we're going to say that 0.5 minus 2x is approximately equal to 0.5. This simplifies our equation greatly because it leaves us with 2x squared times x over 0.5 squared. So we have 4x cubed up top over 0.5 squared, and I can solve that easily. So I get 1.6 times 10 to the minus 5 times 0.5 squared divided by 4. I just collected my terms there and got the x by itself, so I have x cubed. I take the cube root of that value and I get an x of 1.0 times 10 to the minus 2. So using that value for x, we've already assumed that 0.5 minus 2x is about 0.5, but if we plugged in the value for x, I think we would find it's 0.48. For NO, our 2x is going to equal 0.02, or 2 times 10 to the minus 2. And for Cl2, that's equal to x, so that's going to be equal to 1 times 10 to the minus 2. So now we want to check our value for x and make sure that we were allowed to make our assumption. If we take a look at our value for x here, we would find that we assumed away about 4% of the value for the NOCl. We have 1 times 10 to the minus 2 times 2 as x, and we compare that to the 0.5. So generally, 5% is about as much as you want to make in an assumption. And what Le Chatelier's principle covers is a general rule looking at how a reaction will respond in order to restore equilibrium after a disturbance throws a reaction out of equilibrium. So let's take a look at some of the different ways that we can disturb an equilibrium. We can change the concentration of a component. So if we can imagine a reaction that's at equilibrium, and perhaps we add something more to the reaction, or maybe we take something away, how will that reaction respond? If we have a reaction that takes place in the gas phase, either a pressure or volume change can certainly impact where the equilibrium lies for that particular reaction. Or we can certainly change the temperature of a reaction, and when we change the temperature, it affects a lot of different things, and one of the things it might affect is the position of equilibrium for a reaction as well. So if we state Le Chatelier's principle in a very simple manner, we just say that if an external stress is applied to a system that's at equilibrium, the system will adjust or shift to partially offset that stress and restore equilibrium. Let's take a look at concentration changes first. So let's consider this reaction at equilibrium. So we've got iron thiocyanate, which is a red color, iron 3 plus yellow, and the thiocyanate ion colorless. So that reaction there is in equilibrium. It's got a Kc as we see there, iron 3 plus times SCN minus over the iron thiocyanate complex. Now let's say that we've got this mixture at equilibrium, and we add some sodium thiocyanate. Now sodium thiocyanate is a salt. It's going to be a soluble salt since it's a sodium salt and will readily dissolve in water. And when it dissolves in water, we add, in essence, some thiocyanate ion there. And what we find is that this concentration turns more red than it was before. Well, why was that? Well, we've increased the thiocyanate ion. The solution was at equilibrium. We've now increased the thiocyanate ion concentration, and in doing so, we've taken that reaction out of equilibrium. So we've disturbed the equilibrium. At this point, the reaction has too many products. The thiocyanate has increased the amount of products. So this means that the rate of the reverse reaction has increased, and that means that the reaction will shift back to the left or towards the reactants in order to restore that equilibrium. So in shifting to the reactants, we're shifting towards that red complex, and the solution turns more red. Let's take a look at another example here. So the reaction of iron 3 oxide with carbon monoxide is used to reduce iron ore to iron metal. So this is one of the ways that we get iron metal from our metal plants. So we've got iron oxide there, iron 3 oxide, reacting with 3 carbon monoxide gas, and we get iron liquid and CO2 gas. So what we want to do is use Le Chatelier's principle to predict the direction of the reaction following these disturbances. So let's say that we remove carbon dioxide, and I've got these little graphics on here. Hopefully they'll help with the visual here. So we're going to remove CO2. So we are removing a product. Now in our little graphic there, we can imagine the removal of something as a down arrow on that side, and it's going to tip our teeter-totter, and what we want to see is what ways are the balls going to shift. So we shift that down, and the balls move to the right, and that indicates that our reaction will shift to the right. By removing a product, the reaction is going to shift in a direction to replace that product, and that means shifting to the products to replace the CO2 that we've removed. What if we remove carbon monoxide, something in the reactants? Well, in the reactants, so we're removing something, so again we're going to use a down arrow, only this time, since we're removing a reactant, we're going to put that down arrow on the left-hand side. And we see when we move that down, the balls shift towards the left-hand side. So again, when we remove something, the reaction wants to shift in a direction that will replace it. So by removing a reactant, we're going to have a slower forward reaction, and the reverse reaction is going to be faster now, and it's going to try to replace what was removed from that reaction. So here the reaction would shift to the left or shift towards the reactants. Now this one's a little bit tricky, adding iron oxide. And you'll notice that I don't have my little teeter-totter there. Well, if we look at the state of iron oxide there, we see that it's a solid. Now remember, solids are not included in the equilibrium constant expression, and if they're not part of the equilibrium constant expression, then adding or removing those components is not going to affect the position of equilibrium. So it also does not apply when we apply Le Chatelier's principle to the removal or addition of the Fe2O3. The same would also be true as if we removed iron liquid. It just doesn't affect the position of equilibrium because it's not part of the equilibrium constant expression. Well, now we can take a look at how Le Chatelier's principle applies to pressure and volume changes to materials in the gas phase. Now when a pressure change occurs, anything that's in a condensed phase, in other words liquids or solids, are not normally affected because they don't generally compress. They're in a compressed form already. So as a result, their number of moles over volume remains the same, which means that their concentrations remain the same. Gases, however, do compress, and when we compress a gas, the number of moles does not change, but the volume does change. And so by changing that volume and not changing the number of moles, we're actually changing the concentration. We would be increasing the concentration as we compress a gas. So the concentration is going to change most for the species with the largest number of moles. What this means is that when we take a look at how pressure and volume changes are going to affect a reaction, is that when that pressure is altered by a change in volume, there's going to be a greater effect on concentration for the side, either products or reactants, with the greatest number of moles in the gas phase. The reaction will shift to the side with the fewer number of moles of gas when pressure is increased, and vice versa. If we are increasing the pressure by lowering the volume, that increases the pressure on the system. Le Chatelier's principle says that the system wants to offset that increase, and so the system is going to shift in order to decrease the pressure that was added. In doing so, it shifts to the side with the fewest number of moles of gas. So here we have PBS solid plus 3O2 gas goes to PBO solid plus 2SO2 gas. What happens when the pressure is increased? Well, when they increase the pressure there, the reaction is going to want to shift in a way that reduces the pressure. So it's going to shift to the side that has fewer moles of gas. In this case, it's going to shift to the product side because we have 3 moles of gas in the reactant and only 2 moles of gas in the product. So by going to the side with 2 moles of gas, the pressure will be decreased and the change in the alteration of equilibrium, or the disturbance in equilibrium, will be offset. Now what if we decrease the pressure? Well, if we decrease the pressure, then the reaction is going to want to respond to offset that decrease, and it's going to want to increase the pressure. So it's going to shift to the side that has more moles of gas because that will increase the pressure. So if we decrease the pressure, the reaction will shift to the left towards the O2 since there's more moles of gas in the reactant side. What if we mess with volume? What if we increase the volume? Well, if we increase the volume, that's going to decrease the pressure. Decreasing the pressure we saw causes a shift back towards the reactants. If we decrease the volume, that's going to have the effect of increasing the pressure And the reaction is going to want to shift in the direction that lowers the pressure, so that's going to shift back towards the products. Here's another reaction here where we have only one gas there, Cl2, and we would see if we increased the pressure, then the reaction would want to shift to the side with the fewest number of moles of gas. So that would be the reactant side. So if we increase the pressure here, it would shift to the left. If we decrease the pressure, it's going to want to shift to the side with more moles of gas, and it's going to shift back towards the products. Let's look at another example here, or some more examples. We want to know how each of these reactions responds to an increase in pressure caused by a decrease in volume. So we have N2O4 going to 2NO2. So an increase in pressure. So the reaction is going to want to shift to the side with a fewer number of moles of gas, because fewer number of moles of gas is going to lower the pressure. And so we see that on the reactant side, we have N2O4, 1 mole of gas, and in the product side, we have 2NO2, so that's 2 moles of gas. So this reaction is going to shift to the left towards the reactants. Here we have 2CO gas going to carbon solid and CO2 gas. So again, if we increase that pressure, the reaction is going to want to shift in a way that offsets that increase. So it's going to move to the side with the fewer number of moles of gas. Well, we have 2 moles of gas in the reactants, and we only have 1 mole of gas in the products. So this reaction will shift towards the product side to offset an increase in pressure. In this one here, we have carbon monoxide plus H2O goes to CO2 plus H2. In both sides, we see that we have 2 moles of gas. So an increase in pressure will have no effect on the equilibrium here, because whichever way the direction would shift would cause 2 moles of gas to exist. So the reaction here has no way to offset an increase in that pressure, and the equilibrium would be unaffected. Welcome to Lecture 12 for Chemistry 143. We're going to finish up our chapter on initial chapter on equilibrium and move a little bit into acids and bases today. So we want to finish up our talk on Le Chatelier's principle, looking at temperature changes now. So in lecture 11, we were looking at changes in concentrations or changes in pressure or volume, and we saw how they changed the position of equilibrium. But since the conditions of the reaction didn't change, the value of the equilibrium constant remained the same, and that made life a little bit easier to deal with when looking at those types of changes. Now, when we're changing temperature of a reaction, that very often affects the value of little k, which is going to affect the value of the equilibrium constant, big K. However, we can still predict the way that the reaction is going to shift in order to restore values to fit the new k for the new temperature, whether the temperature is raised or lowered. So what we need in the data we need in order to see what type of change temperature has on the value or on the position of equilibrium is we need that the delta H, that change in enthalpy. And remember we have two different types of reactions in terms of enthalpy. We have endothermic or exothermic. So if a reaction is endothermic, then heat is being absorbed by the reaction, and we're going to treat heat then as a reactant. And so if we want, we can even take a reaction and say plus heat over on the reactant side if it's endothermic. If it's exothermic, then heat is put out or produced, and we can treat heat as a product. And so over on the product side, we can write plus heat on a reaction there as well. So now that we've got heat as either a reaction or a product, when we increase the temperature, it's like adding heat. It's one of the ways we increase temperatures is to add heat to a reaction. And so we want to see, is it going to shift to the left or is it going to shift to the right? And depending on where we have heat added into the reaction is going to determine which way that reaction is going to shift. And if we decrease the temperature, well, it's like removing heat. So it's just like adding or removing a reactant or product, and we treat it accordingly. Let's take a look at an example here. Let's consider this reaction here. N2 plus 3H2 goes to 2NH3. We see that we've got a delta H of negative 92.2 kilojoules. And so we have an exothermic reaction. So we would want to write plus heat on the product side. So let's just go ahead and do that there. So I'm going to change to a red pen here. We're just going to say plus heat over here on my product side. And now we can see, look at the value of the equilibrium constant as it changes with temperature in this graph. We see that as the temperature is increased, the equilibrium constant decreases. And this is because as we increase the temperature, we're adding heat. And as we're adding heat, we're causing that reaction to shift in that direction. So at equilibrium at higher temperatures, we have more reactant than product, and that results in a lower equilibrium constant. And we see that with these values here in this table. Okay, as that temperature goes up, that equilibrium constant is shifting more and more towards the reactants because we treat heat as a product because we have a negative delta H. So here's a different reaction here. We've got N2O4 going to 2NO2, so just a decomposition of N2O4 reaction. And N2O4 itself is a fairly colorless gas, whereas NO2 has a very rich brown color. And we have two different test tubes filled with these gases here in equilibrium. So here we see at the colder temperature, because we do see here actually that we have an endothermic reaction, so let's put plus heat over here in the reactant side, and we have our mixture there in an ice bath, and we see the color is fairly light, and the reason for that is as we have lower the temperature, that has the effect of removing heat. So if we're removing heat, the reaction wants to replace it, and it's going to shift the reaction that way. Now, if we have just room temperature here, which is just the blue arrow right there, room temperature we see is a little bit darker. So we've warmed that reaction up just a little bit from the ice water, and so it shifted just a little bit more in that direction, because if I'm adding heat, the reaction wants to get rid of it. Since it's a reactant, that's going to make it shift more towards the products. And then here with my green arrow, we've got this vial here in hot water, and we can see that we have a much darker brown gas mixture there. So we've got a lot more NO2. So we've added quite a bit of heat to that reaction, and the reaction wants to shift now way towards the left because we're adding heat, which has the effect of adding a reactant. That makes the reaction want to shift towards the products, and that's going to give us a darker brown color. Well, a little bit off of our Le Chatelier's principle topic here. This is a harder example of a way to work K, equilibrium constant problems. And you may run into a problem like this on your homework. So here we have an equilibrium mixture of 3 different gases. They're in a flask, and they're at equilibrium already. And then we're going to disturb that equilibrium by adding a reactant, one of our reactants. So in a way it is Le Chatelier's principle, because we're adding a reactant to something that's already at equilibrium. So we've disturbed the reaction, and all we've really done is made that shift. In the past lecture, all we really did was treat Le Chatelier's principle very qualitatively, saying, well, which way is it going to shift? Well, we added a reactant, so this is going to shift towards the product, but now we want to treat it a little bit more quantitatively to see what's going to happen. And this is something that I will work out in class. Well, that finishes out Lecture 15, our introductory chapter on equilibrium. This next chapter, now if we go way back is going to focus chemistry history, on the equilibria before we really had any way of doing any kind of elemental analysis. One of the things that chemists were noting is that a lot of the reactive acids tended to contain oxygen. So these would be things like sulfuric acid, H2SO4, nitric acid, HNO3, phosphoric acid, H3PO4, etc. These are what we call oxoacids. Later, it was noted that there are some other reactive acids that do not have oxygen in them. Instead, they have hydrogen and a halide. So we've got hydrogen chloride, HCl, hydrogen fluoride, hydrogen bromide, hydrogen iodide, all very reactive acids. So Svante Arrhenius, who we spoke about earlier, looking at kinetics, he was really the first to notice that there was a link between all of these different acids, and it looked like they all contained hydrogen. So he first proposed that it was the hydrogens that were making things acidic. So we had the Arrhenius theory of acids and bases, looking at whether or not something had an H plus in it, or for bases, why, if it had an OH minus in it. However, the Arrhenius theory was not terribly complete, and it had a difficult time describing why a substance like ammonia, NH3, had base properties, since it did not share any characteristics with the other common bases, such as sodium hydroxide, potassium hydroxide, lithium hydroxide. All of those original Arrhenius bases all had metals and hydroxides. Ammonia has none of those, but still has the same base properties. So sometime later, a theory was brought about, the Bronsted-Lowry theory. This still supported the Arrhenius theory. However, it expanded its capability of bringing in other compounds that also had acid-base properties. So Bronsted-Lowry acids are now defined as compounds that donate a proton, which is just going to be an H plus, during a reaction. And our Bronsted-Lowry bases are now defined as compounds that would accept a proton during a reaction. So if we look at these definitions really close, we'll notice that they're not specific to that substance's just intrinsic chemical properties or its chemical makeup. We don't care if it has an OH in it or not. We don't care if it has an H in it or not. The key here is that we're looking at its behavior during a reaction. Does it accept a proton or does it donate a proton during a reaction? And that's what's going to determine if it's going to be treated as an acid or a base. So the other implication this has is that it means something, a compound, cannot be strictly defined as either an acid or a base. We can't always say that this is an acid or that this is a base, period. There are several compounds that can behave as either an acid or a base. So let's take a look at an example here. This is just acetic acid, CH3CO2H plus water, and it gives us the acetate ion and H3O plus. So here we see that the acetic acid has lost a proton here. Let me bring up my drawing thing here. So this H is no longer here. Okay, so this has gone to the water, and water has become the hydronium ion. So my acetic acid has donated an H+, which makes it an acid. Water has accepted that H+, which makes water a base. We don't normally think of water as a base, but again, we're just looking at its behavior in the reaction. So water behaves as a base. Now, the other term that we haven't heard about here are the products here. So our acids always have conjugate bases, and bases always have conjugate acids. So your conjugates are always in the products, and they always differ by just a single H+ from their parent compound. So in Bronsted-Lowry theory, we're going to have acids and bases, conjugate bases, and conjugate acids. So again, here we want to say what lost an H, and we see that it was the acetic acid. What gained an H+, and we see that it was the water. So that's why we define water here as a base. Let's go back to the bugaboo of the Arrhenius acid-base theory, and that's ammonia. So ammonia was one of the primary compounds that led Bronsted and Lowry to develop this theory, and they actually developed it independently. They weren't working together, but they came up with the same basic concept around near the same time, so they're given joint credit for it in the history books. But it was really ammonia having its base properties and not fitting into the Arrhenius theory that prompted their new theory. But now with the Bronsted-Lowry theory, we have a way of describing of why ammonia has acid or has base properties. If we look at what ammonia does in water, that we got NH3 and H2O. It takes an H+ away from water and leaves us with NH4+ and an OH-. And now if we look at this reaction, we see that water has lost an H+, and here we would treat water as a base. So now in the last two reactions, we've categorized water as an acid and we've categorized it as a base. It just depends on what it is in the reaction with. So because water can go both ways like that, and it does so fairly easily, we would classify water as being amphiprotic. And that just means that it can either lose or gain a proton and act as an acid or as a base, depending on the conditions. Well, earlier, in this earlier slide a couple ago, we introduced this term of a conjugate. We had conjugate acids and conjugate bases. So your conjugate acids and bases are the compounds that have the acid and base properties in the reverse reaction. So if we have what we call weak acids and bases, and we'll talk about those later, we are always going to have an equilibrium situation set up in our acid-base reaction. So if we have an acid and base in the forward reaction, we're also going to have an acid and base in the reverse reaction. So we saw in that reaction a couple slides ago, acetic acid and the acetate ion make up a conjugate pair. In the forward reaction, your acetic acid was acting as the acid. In the reverse reaction, the acetate ion was the conjugate base. So acids have conjugate bases. For the other compound, water, we saw water was acting as a base and becoming H3O+, and that's its conjugate acid. So in a reverse reaction, H3O+ would be acting as the acid, and H2O would become the base on the other side. So if we look at these two compounds, we see that our conjugate pair only differ by that single H+, and that's key. It can only differ by a single H+. So we'll expand on this idea of conjugates a little bit in the next lecture, but that finishes out lecture 12. Some difficult concepts to make sure you read up on, and as always, if you have any questions, please make sure you contact me.